I call this is lesson 4.10, models of matter continue to develop. So there's this whole branch of physics which we would call modern physics. Even when you start to take a look at things like quantum mechanics, yes, that is more modern than classical physics like Newton's laws of motion. But when we're talking about the modern physics here, we're not talking about things like quantum mechanics or de Broglie wavelengths. We're talking about really, really modern models, which date to about, I know it's going to seem like a contradiction to you, about 1965 or so, is when physicists started to really, really delve down and come up with better models to explain matter. Today what we're going to be doing is talking about matter and antimatter and how they're related to mass and energy. And then we're going to be talking about some of the science that I guess goes into coming up with these new models of matter. In 1929, so almost 100 years ago, a physicist by the name of Dirac hypothesized the existence of antimatter. And what he suggested was that for every particle that exists in the universe, there is a type of particle that's its antiparticle. And we've talked a little bit about this before. I'm not saying for every electron in the universe there's an anti-electron someplace. I'm not saying it's a one-to-one ratio. What I'm saying is since electrons exist, anti-electrons exist. And the hypothesis that he came up with basically said that's true for any particle. So for example, there is an antiproton, and that has turned out to be true. There is an anti-electron, and we should know, or you should know what an anti-electron is. It's a beta particle. An antiproton we haven't really talked about. And at a very elementary level, you would probably be told the reason why a proton and an antiproton are a particle-antiparticle pair is because they're identical in every way except for charge. Okay, that's what you would be told. And the same thing with an electron and an anti-electron. You would be told, well, every property of those particles is the same except they have opposite charge. Go ahead, Armand.
How can a neutron have an anti-neutron?
Well, that's what I was just going to get into. That on a very basic level, the question is being asked, how does that work for a neutron and an anti-neutron? And I guess what I would tell you is there has to be a bit of a lie there somewhere. It has to be more complicated. Now, I will tell you right now that a neutrino has no charge. That's a fact. So we have an issue here with an antineutrino in that there has to be some other property that's opposite. And it isn't charge. It turns out it has to do with a property of matter that we don't study in high school physics very much called spin. So particles have charge. They're either positive or negative, and they also have spin. And you can think of spin as being, I don't want to throw words at you because they might confuse you. Spin as being either this spin or that spin. Okay? And there's more than two types of spin. Okay? They're numerical values. You can have a spin of 1, of 1/2, of -1, of -1/2. There's all kinds of weird things going on. But your question is a great one, because it leads to this, that I'm going to tell you the reason why a neutron and an antineutron are a particle-antimatter particle pair is because they do have opposite charges. And I know it seems like I'm contradicting myself, because I just kind of admitted that a neutron has no charge. But it turns out there are pieces of a neutron that have charge, which we will learn about tomorrow. And if you take all of the pieces of a neutron, I use the word pieces loosely. If you take all of the pieces of a neutron and you add up their charges, there's some positive charge and negative charge, and it happens to add up to give 0, which is why a neutron is neutral. And if I could take all of those pieces that make up the neutron, and they all have charge, and I change their charge, if it was positive, I changed it to negative, and if it was negative, I changed it to positive, and I added them up, I'd still get 0. Okay. If I told you that in a neutron, I just wanted to make sure I had that right. That there were three particles, and there are, I'm not lying to you, there are three particles that when they get together, they're a neutron. And one of the particles has a charge of 2/3 elementary charges, so I'll stop right there and say, you know what? Millikan was wrong. There are charges that are not multiples of the elementary charge. I tell you inside of a neutron, and this is a great question because it's going to lead to all kinds of stuff in today's lesson and tomorrow's lesson. There's a positive 2/3 elementary charge particle and a negative 1/3 and another negative 1/3. There's three particles, which, does anybody know the names of them? They are quarks. Okay. When I add those numbers together, positive 2/3 plus negative 1/3 plus negative 1/3, I get 0. And what I'm telling you is the reason why an antineutron is an antineutron is because it has three antiparticles inside of it whose charges are the opposite of the three particles that are inside of a neutron. But when you add those numbers together, you still get 0. So sometimes, Armand, the reason why a neutral particle has an antiparticle is it's not a fundamental particle. There are pieces within it that have charges. But sometimes, like with the neutrino-antineutrino, it's a different property. It's not always just about charge. It very often is about charge, but not always. Have I answered your question? There's a reason why Millikan was not able to see evidence of these charges, and I'm going to talk about that today. So, going back to the script here, I suppose, Dirac comes up with this idea. Since then, there may be certain particles in modern physics and particle physics, because I'm not 100% up on all this. It changes year to year. There may be some antiparticles that have still yet to be discovered. Okay, I don't know. But the standard model of matter basically says, in order for all of our hypotheses to make sense with nature and what we observe, every particle must have an antiparticle. And again, the way I say that, I don't mean to imply there's one antiparticle for every particle in the universe. I mean, if there's a particle called a muon, then in our universe there are particles called antimuons. Well, we call them antimuons. They're opposite in some way to a muon. Any questions on matter-antimatter in this context? And they don't have to be questions for clarification. They can be questions about, well, what about type questions, or I'm curious type questions. Okay, so when matter and antimatter collide, it's called matter-antimatter annihilation. And the word annihilation, you know, in the English language, if you're reading a book and it says the army was annihilated, it means they were obliterated, they were decimated. Well, decimated means something different. It means they were severely damaged or broken down. But the word annihilation here means absolutely removed from the existence of the universe. It's not that they're hammered up into smaller pieces and spread out over something. They just cease to exist. But you cannot just destroy mass. It's not because mass is always conserved. It's because mass energy is always conserved. And if you lose mass in any type of change, you lose energy. And literally, I know I'm going to get a little off topic here, but for you chem people, that means any exothermic change, and don't start an argument with your chem teacher about this, but every exothermic change, the mass of the products is going to be less than the mass of the reactants. You're going to still have the same number of atoms and everything, but the mass of everything will be less. Not noticeably, because the energy in a chemical change is, we saw that yesterday, right? Chemical change was almost zero compared to fission and fusion. So this formula that's on your formula sheet could be used to find the energy released when matter and antimatter collide. All I have to do is feed the total mass in here for delta M that disappears from the universe, and I get the energy that appears in its place. When matter-antimatter annihilates, you will always produce 2 photons. And there is a reason for that I will talk about in a second. So you have 2 particles, like maybe a positron and an electron, or they have to have mass. Can't be a neutrino and an antineutrino. A proton and an antiproton. A neutron and an antineutron. You will get 2 photons. So the first thing we want to look at is what this means visually. There's a reason why you need 2 photons, and it's the only reason why I'm drawing or giving you this diagram to consider. The 2 photons each have momentum. They each have momentum. Compton discovered that. When I have an electron which is negative and a positron which is positive, and they come into contact, they will be moving towards each other when they come into contact. Even if they just appear out of nowhere and are already heading kind of in this general direction towards each other, they're attracted to each other. So their overall motion will be towards each other, which means the positron has momentum to the left, the electron has momentum to the right. Momentum's always conserved. You cannot get 1 photon, because you're bound to be able to come up with scenarios where the total momentum before in that situation has to be 0, because they're coming towards each other. So that's what's going on, and that's why you need 2 photons. I guess we never answered the question, did we? The question is, find the energy produced and the wavelength of the 2 photons produced when an electron and a positron collide. Well, our mass here is 2 multiplied by 9 times 9.11 multiplied by 10 to the negative 31 kilograms. And that mass is going to be our mass change. Now, technically this is not correct. The mass change is actually that. It's the negative of that, like you and I were talking this morning, Charlie. Is it that important that you include the negative? Well, no, because after all, we're just after the energy. So that works out to, I believe, 1.822 times 10 to the negative 30 kilograms. Am I right? Okay. So we feed that into our formula for change in energy. It's equal to the change in mass times the speed of light squared. So we're going to take 1.822 multiplied by 10 to the negative 30 kilograms times the speed of light squared. So we're getting 1.64 times 10 to the negative 13 joules. That's the energy shared by 2 photons. So we're going to have to divide that by 2 to talk about the energy of a photon. If you're really following along, since we were asked for the energy of each photon and the wavelength of each, we could have just used the mass of 1 electron. Because you have 2 electron masses, I mean an electron and a positron, but you have 2 electron masses in terms of numbers producing 2 identical photons. I don't know what the accounting is like, if it's like this mass goes to this photon and this goes to that. It's not important. But we're going to divide that by 2 and get, I'll write this down first, 1.63 times 10 to the negative 13 joules, which works out to 8.199 times 10 to the negative 14 joules for each photon. And if we want to find the wavelength of that photon, then we set that equal to hc over lambda, because the energy of a photon is hc over lambda. You know, I suppose you could do the 1242 thing and work in EV, but that's only really useful if you're talking about infrared, visible, ultraviolet, like that kind of range. This is quite a large amount of energy. I don't know if you're comfortable with this idea yet, but visible light photons are in the neighborhood of 10 to the negative 19 joules. And they are usually 1 or 2 eV in that neighborhood. So we're talking here about millions of eV most likely. So for that reason, I'm simply going to use standard units. I'm going to take hc in standard units of joules seconds and meters per second, and I'm going to divide by the energy in joules. I'm not messing around with eV. I mean, I can look at that number right now and say that it's, maybe it's not a million, but it's 100,000 eV. More than 100,000, probably about 400,000. So 6.63 multiplied by 10 to the negative 34, multiplied by the speed of light, divided by my answer, gives me 2.4 times 10 to the negative 12 meters for a wavelength. That's gamma radiation. Given that X-ray is 10 to the negative 10, and gamma is the only one with a shorter wavelength than X-ray, this is gamma. All right? So any questions with the first example? Charlie?
So, is the reason why we have antiparticles is so that it can create energy once it hits the two, or is there no energy? Like, sorry, I'm confused.
I think you might be asking two things. First of all, the reason why antiparticles exist, period, has to do with, it's the same thing as why do we have antineutrinos that we talked about the other day, or neutrinos. It's that when physicists start to analyze changes, nuclear changes, which we'll talk about the science of today in terms of how they do that, they either discover other particles in their investigation, or when they look only at the particles they can see, something isn't matching up. It would be like me looking at my bank balance on my phone and then me getting a bank statement. I mean, nobody gets bank statements anymore. But if my bank statement were not matching my balance, I would be looking for something I wasn't aware of. And it was, oh, right, I spent $80 on a pinball machine at a garage sale. I don't know, whatever. That would be a great find. Anyway, that's why they exist. They exist because it turns out they're needed to explain observations. That's maybe the wrong way of putting it. They're needed to conserve momentum and to conserve energy and to conserve charge and all of these other things. If you're asking why does it have to be a particle and an antiparticle to create the energy, I don't have an answer for that. Particles will not disappear from the universe on their own. They need to do it with antimatter at the same time. Did you feel I've answered your question?
Yeah.
Okay. And never feel afraid to ask a question. Any other questions about example 1 or matter-antimatter annihilation? All right, well, the opposite can happen. It turns out that matter can spontaneously come into existence at the expense of energy. But when that happens, it's called pair production, first of all. You will always produce a particle and an antiparticle. And we're going to stick with producing an electron and a positron. But it turns out when it happens because of one photon, not two. So when matter and antimatter collide, you get two photons. But if you have a single photon with the right frequency or wavelength or energy, under the right conditions, it can disappear and in its place you will find two new particles in the universe, which, by the way, are antiparticles, which they're going to be produced, and we won't worry about exactly why right now, but they're going to be produced moving away from each other. And they're going to move in opposite directions where the antiparticle is bound to run into some particle and annihilate itself. Because our universe has much more matter than antimatter, we don't see antiparticles living very long in our universe because of this. As soon as I create a positron, it's going to bump into an electron somewhere and disappear. So it's this weird cycle. Nature producing these antiparticles only to remove them from the universe again. What has to happen is a photon has to get close to a nucleus. It's complicated, and I don't want to get into the details of it. A photon has to get close to a nucleus, and it will be absorbed by the nucleus, and at the point of absorption, you get these two particles being created. So here's a visual of what we're talking about. We've got a photon getting very close to a nucleus, and afterwards you have the two particles being created moving away from each other. Now, they are moving away from each other, and I don't know that you need these details, but you never know when you might be asked on a diploma exam. They are moving away from each other because if you look at the photon has momentum in the downward direction. The photon has no momentum left or right, which means afterwards the total momentum has to still be down. We have to have equal but opposite momenta left and right. And this is the picture that you see in textbooks all the time, and I never really thought about it until the student asked, why aren't those two angles the same? Because you can see that the positive particle is is produced with more momentum to the left than the negative particle is to the right. Does anybody know why? Do you?
Would the nucleus be pushing it away?
Well, I would phrase it a different way. The nucleus has momentum as well. So there's zero momentum left and right for the photon, which means however much momentum there is to the left is the same as to the right, because it adds to zero left, right. And this positive particle is the only one that has momentum to the left, which means the negative particle and the nucleus both have to have momentum to the left. And because the mass of the nucleus is so large, even though it doesn't move much, that momentum is significant. Well, it doesn't matter. The momentum is significant. Momentum is momentum. So if you're wondering about why the angles seem off, that's why. Now, what are we asked for here? We are asked to find the photon's energy, or the minimum frequency of the photon required to produce this. Well, in this case, what we have is we have a single photon with hf of energy. That's the energy before. Afterwards, there is no energy. The photon is gone. Where did the energy go? It was converted to mass. So this time what happens is the energy in the universe drops and the mass goes up to compensate. And this is then going to be the change in energy. And if you want to be very clinical about it, whatever HF is the negative of the change in energy, right? Because the change in energy is negative. And that's going to be set equal to delta M c squared. But we know what delta M is. It's the sum of those two masses. It's that number that's probably still on my calculator here. No, I don't know that I ever had it on my calculator. It was 1.822 times 10 to the negative 30. Am I right there in my memory and calculation? This is the total mass that all of a sudden appears. So if I multiply that by the speed of light squared, I get the change in energy. And you know what? I could just ignore it, but I don't like it when I make a mistake. This is an increase in energy. When you look at it in the right way, this is an energy added to these particles to give them mass. And that's why the mass goes up. I wouldn't get hung up on the positives and negatives here. Anyway, if that's the energy of the photon, then I can set that equal to HF. That's the energy equivalent of the two particles that are created, which means it must be the energy equivalent of the photon that created them. So this is what I set equal to HF. In other words, I have to divide this by Planck's constant. And I'm just not used to seeing frequencies that large, so can you confirm that you're getting the same frequency? Okay. Just, you know, we play around with 10 to the 14, 10 to the 18, 10 to the 4. All of a sudden we get 10 to the 20. We forget that gamma radiation has quite a high frequency. So that's the frequency. That's the answer to the question. However, why? And Alex, you got a nice clear voice. Can you tell me what that frequency was? Do you have it?
2.47 times 10 to the 20.
Let's even assume that that's an exact frequency and there was no rounding involved. Okay? Why does it say what's the minimum frequency? And there's a couple of very important things to point out about why it says minimum frequency.
Does it have to be enough energy to create the mass?
Right. If it has less frequency, if the frequency of the photon's less, then it doesn't have that energy that's the equivalent of two masses of those particles. That's why it's minimum. If it's less than that, you just don't have enough energy, and for whatever reason, it won't be absorbed and those particles don't come into existence. But minimum, that adjective minimum on the frequency implies that it can be more than that, and it can be. If the frequency is more than that, then that means the energy is more than enough energy to create that matter. Where does the extra leftover energy go, do you suppose? Craig?
Smaller photon. Is it another photon, but it's like less
Oh,
than?
good idea. It turns out no. It's not like the Compton effect where you have some leftover. In pair production, even if the frequency is more than the minimum, and it almost sounds like the photoelectric effect, doesn't it? But if the frequency is more than the minimum frequency needed, the photon is still absorbed. There is no more photon. So where could the energy go then? Do you know, Anna? That's another option that makes sense, but it turns out is not true. Into creating another mass. It turns out no. So the photon is absorbed completely and there is no photon afterwards. And the only two particles that are created are the electron and positron. Yeah, it's kinetic energy of all the moving pieces. In fact, you know, in principle, if you're exactly at that minimum frequency, the particle and antiparticle will be created and they won't even have any motion because there's no energy left to push them, and then they'll just annihilate again. In which case you get a single photon turning into two particles very briefly, which annihilate, producing two photons. But more often than not, it's a greater frequency, and any leftover energy just goes to kinetic energy of the electron, the positron, and the nucleus. Right? Any questions about example 2? Example 3, the annual electrical energy usage of North America is about, now I researched this maybe 4 or 5 years ago, I'm sure it's changed, is about 3 times 10 to the 19 joules. if we could develop a matter-antimatter generator, electrical generator, which is, by the way, we don't have antimatter. You don't go to the store and buy antimatter. You'd either have to find a pocket of it someplace in our universe that's been untouched by matter, or you'd have to create it. But the energy required to create the antimatter is going to be the same as the energy you get back in using it, so it's a dead end. You'd have to find a pocket of antimatter someplace that's isolated from everything. But if we could, take a barrel and dump in the matter, and take another barrel and dump in the antimatter, and gradually mix them together to get the energy out. At what rate would mass need to be converted to energy? Well, this energy is equal to the change in mass needed multiplied by the speed of light squared. And I want to say that when we divide by the speed of light squared, will be 3.3 repeating times 10 to the 10. 11? 10. So you're taking that energy and dividing by the speed of light squared. No, my mistake. You're getting 3.3 times 10 to the 2. You're getting 333 kilograms. The size of a very small car. Really small car. Under 1,000 pounds. And that's per year. Let's work out what it is per second. What would be the rate in kilograms per second that we would have to feed the matter and antimatter into this machine to run everything in North America? Well, I'm not going to show all of these numbers by writing them down, but I'm going to take 365. There's a lot of ways to do this. 0.25 times 24 times 3,600. There's 24 hours in a day. I'm multiplying the number of days by 24 to get hours. Each hour has 3,600 seconds. So this is how many seconds a year is. Certainly not a number that we recognize. We don't use that number often. So if I take 333, let's be generous and say 0.3 repeating kilograms divided by that many seconds, that's how many kilograms of matter-antimatter combined would need to go into the machine per second to keep everybody happy with their electrical needs. 10 micrograms per second. And the point I want to make is, other than you might be asked this on an exam, the energy stored as matter is immense. That's why nuclear changes produce so much energy. Any questions with example 3? I'm not optimistic that we will be anywhere near this technology before the sun engulfs the earth. Happy thought for a Tuesday afternoon. Got billions and billions of years. We'll move to some other planet by then. So now, any questions? Of course, the other planet may be in the process of being engulfed as well. It's all going to end someday.
We won't be there to see it.
No, that's right. Maybe we will have evolved to be ones and zeros. All right, okay. Particle physicists routinely smash matter to discover previously unknown particles. This reminds me of being a child. And it would really upset my parents that I would get something for Christmas and within a week it would be in pieces. Because I was curious. I remember this toy car, it had batteries in it, and the remote control, this sounds almost weird, was this thing, this plastic thing that you would squeeze, and all it did was it pushed air out of it into a tube that went into the car somewhere. And by squeezing it a certain amount, you could go forward or you could go backwards. By squeezing it a different amount, you could go forward and turn left. There were no wires. You were just pushing air into it, and somehow it worked. Well, I had to find out how it worked, so I would take it apart. And that's what physicists do. They smash stuff together to discover things that they had never seen before. So there's two issues here. If you want to break apart matter, the forces holding matter to itself are immense. You need a lot of energy. You need a big hammer. The other issue is these things, if there are new pieces that come flying off, they're invisible. I don't mean invisible in the science fiction sense. I mean they're too small for us to see, even under a microscope. So there's two problems that have to be overcome. One is, how do you provide enough energy? And two, how do you detect the particles? Well, you use a particle accelerator. Particle accelerators make use of electric and magnetic fields to move particles around and speed them up to higher and higher and higher speeds. Since things with charge are the only things that electric and magnetic fields can affect, anything that's in a particle accelerator has to be charged. You cannot accelerate neutrons and smash neutrons together with electric and magnetic fields. We're talking here, if I were to say 20 years ago, we would be talking billions of electron volts. And about 10 years ago, we cracked the trillions of electron volts barrier with the Large Hadron Collider. And there's two types of these particle accelerators, a cyclotron and a synchrotron. And I'm going to go through the workings of each of them. You don't need to know this, but sometimes on a diploma exam, you're given a diagram and it says synchrotron. If you've seen it before, you know what's going on. So first of all, a cyclotron is fairly small. We could have a cyclotron on this table. I might need more support under the table to hold it, but sometimes they're about this big. When I was talking about that technetium 99M that they injected me with, they produced that in a cyclotron. And in fact, that was how it was first discovered, and the diameter of the cyclotron, I think, was 37 inches, which is a yard, which is about a meter. So it's pretty small. What they do is they use a varying voltage. It's called a square wave electric field, and I'll explain what that is in a second. And they inject a proton right here at this point. Okay? So there's a proton or a stream of protons that enters there. And what happens is the proton enters through a little hole in this disk, half disk in the top right corner. And at that instant in time, things are timed so that this plate is negative and this plate is positive. So what happens is that accelerates the proton across the gap, and now the proton is moving faster. You with me? So when I say you need to be able to work with this, if I told you that voltage, you could find the speed reached. Right? At that point in time, there's a magnetic field, and the magnetic field is towards the top of the page. So which way is the proton deflected? Well, it's moving kind of this way. And if you're watching this on video, I'm using a right-hand rule. And the magnetic field is up, which means it's forced kind of out towards you. So it's going to travel in a circular arc through that other disk. And it's timed so that when the proton ends up here, moving that way, the polarity is switched. That's what this square sine electric field thing is about. It's a voltage in one direction, then it flips to the other direction, then it flips to the other direction. So at this point in time, the proton is traveling this way. It's going to accelerate across that gap, being attracted to the negative plate, where it will travel in a larger radius. And the thing just keeps repeating, repeating, repeating. This has, I guess, 1, 2, 3, 4, 5, 6, 7, 8 or 9 accelerations. You're probably talking about hundreds or thousands of them, though. And the result is it spits the proton out that end. So you can have over here something that you want the proton to smash into. You can put two of these together and smash protons into protons and reveal that there are particles inside of a proton, quarks. But you need a big hammer to reveal them. So that's a cyclotron. Any questions? There's a diagram of one from some physicist notes. Looks like it's probably done 100 years ago. There's a cyclotron. Like that's a 1 foot long ruler, 12 inches, about 30 centimeters. They're tiny. Bigger one. I don't really have anything for reference here, but it looks as though this is maybe a guardrail for people so they don't fall over, or maybe ladders, so it's quite a bit bigger. There's an example of one in a museum in France. I don't know who that gentleman is, but thank you for the use of your photo. Now let's talk about a synchrotron. A synchrotron also makes use of electric fields and magnetic fields. The magnetic fields primarily to change the direction. Primarily to change the direction of the path of the beam of particles. The electric field rather is used to accelerate the particles to quicker and quicker speeds. But things are synchronized so that every time the particle is given a kick, the magnetic field is increased to keep it in that same radius. So it's not spiraling out. It's given a kick, going faster, so the magnetic field goes up to pull it in that same radius, given a kick, and the kicks are given in between these black rectangles. So when the particle, let's say it's a proton, is here, moving in the magnetic field deflected in this direction, this is negative and this is positive. There's still a lot of timing that goes on. And this might be given hundreds or thousands or millions of kicks. Each time it's given a kick, the energy given to the particle is more. So if you get into the tera electron volt range, that's trillions of electron volts, these things are really moving. These are huge. This is a synchrotron in Soleil, France. I don't know how I pronounce that, good or bad, I don't care. And you can see vehicles over here. They're huge, huge. If you've heard of how many of you have heard of the Large Hadron Collider? I think the diameter is, Alex is going to look it up. I want to say the diameter is 13 kilometers. We'll see how good my memory is or my intuition is.
Diameter? You asked for the diameter?
Diameter. That's fine. And by the way, the Large Hadron Collider is built underground. You get in an elevator, you go down underground, and it's this immense thing that's built underground. We'll come back to that once you find it. So here's a better picture near the bottom right. You can see, because it looks like an ambulance of some kind. I hope everybody was okay. Do you have a question? Yeah, it's not a single particle. It's a particle beam. So what's happening is they're feeding a whole bunch of, I'm going to stick with protons because it's easier to explain, a whole bunch of protons. It turns out that technetium-99m that was medically produced for me, there are 2 or 3 reactors or particle accelerators in North America that provide 40 to 50% of the world's needed technetium-99m. And I did a little research after our conversation. Technetium-99m is the most used radioisotope in medicine. It's used for lots of things. And due to some supply issues in 2009, the whole world went into kind of a shutdown with that stuff. They couldn't get enough of it. And it's because they bombard molybdenum. I don't know if that's pronounced right. Doesn't matter. They bombard molybdenum-99 with hydrogen-2 in a particle accelerator, and they produce another isotope of molybdenum, which then decays over 6 hours with a half-life to produce the technetium-99m. So they have this beam of stuff, H2, hydrogen-2, hitting lumps of molybdenum, I think it's molybdenum, and then they're collecting somehow all of these pieces, which have a half-life of 6 hours, and trying to get it. I think the half-life of the product is maybe 6 days, and then they collect the technetium. Anyway, it's a beam. It's not just one particle, and it doesn't have to be a proton. Yep. Any other questions about synchrotrons? Yep.
What happens if you get stuck in one while they've got the beam going?
Well, it's funny you should ask. Anatoly Bugorsky worked with the largest Soviet particle accelerator. It was called the U-70 synchrotron. And I'll paraphrase stuff here. He was checking a malfunctioning piece of equipment when the safety mechanisms failed. So I don't know what kind of safety mechanisms they would be. I would imagine that, there's gates, and when the gate opens, everything shuts down. I don't know exactly. This is 1978, so this is ancient history as far as you're concerned. Okay. He was leaning over the equipment when he stuck his head in the path of the 76 giga electron volt proton beam. So it's not a single proton, it's just a big stream of them. And they're moving, giga electron volt. Giga is 10 to the 9. Yeah? Now, we have a problem here because at this energy, maybe the formulas we use aren't valid. We would have to use relativity, but I'll deal with that if that happens. So 76 giga electron volt in joules is this many. It's going to be relativistic, so we're going to have an issue here. If I multiply that by 2 and divide by the mass of a proton, it's not going to work. And if I use the traditional way to find the speed, what I'm getting is a speed greater than the speed of light. The formulas we use in high school physics won't work because the energy is too big. I know how to calculate the speed, but I don't want to spend time doing it. It's moving very fast. Okay, maybe, let's just say half the speed of light. So you get this beam of protons moving at half the speed of light. This guy sticks his head in there. Imagine that somebody could turn the beam off as soon as the first particle hit his head. At traveling at the speed of light, how many particles are going to go through that guy's head in that half a second it takes you to hit the switch? Lots. That's the answer to the question. So I'm so glad you asked. Reportedly, he said he saw a flash of light, which, that's interesting. It did something to his brain. You can't see this beam. It isn't that he looked and he saw the beam coming towards him. But when it passed through him, he saw a flash of light, but he didn't feel anything. And in fact, from some accounts, he didn't even know anything had happened for a few seconds, okay? Because there was smoke and burning and a hole in his head. So the left half of his face swelled up beyond recognition, and over the next several days, the skin started to peel, revealing the path that the proton beam, they're saying near the speed of light. I'll find out a little later. Burned through parts of his face, his bone, and the brain tissue. So there's a photo of him, and there's superimposed on it, I'm assuming, is a line showing the hole that went through his head. And when you look at the top view, it went through his brain. As is the case back then, 1978, with stuff like this, it was like, well, okay, sorry, buddy, let's just put you into hospice and, hope for the best. But he survived. He survived. He completed his PhD. Intellectually, he was fine, but he was tired all the time. This was the long-term effect. I'm not saying, and there's not a lot of clinical trials with this, I'm not saying it wouldn't kill somebody else, right? Loss of hearing in the left ear, replaced by a form of tinnitus, which is a constant ringing in your ear. Paralyzed left face, so there were physical damages. And he suffered from different types of seizures from time to time. But from what I understand, he lived, I don't know, ripe old age is maybe the wrong thing to say. I don't know how long he lived, but he didn't die because of this. He lived his life. I don't think it's a matter of ionizing DNA at this point. I don't think this is the kind of radiation we're talking about where it's going to cause cancer. I think this is just a series of very tiny bullets going through in the same line through your body, damaging it. Some people claim, and again, there's not a lot of science to this because it doesn't happen very often. Some people claim that it was the sheer speed of the particles that saved him because the heat generated would have automatically cauterized any wounds, which is an interesting idea. Does that answer your question? Okay, so be careful leaning into particle accelerators. So now, how do we detect things? Don't forget I'm talking here, everybody, about the science of learning stuff, that you smash stuff together and the pieces come flying off and you want to detect them. So first of all, the two detection devices we're going to talk about will only detect particles if they have a charge. And one is called a bubble chamber and one is called a cloud chamber. And I don't believe you need to know exactly the difference or how they work. I'm going to explain that anyway in a second, but when you have a charged particle moving through a cloud chamber or a bubble chamber, it leaves a track. And what the track is caused by is the charged particle in some way ionizing the material it's passing through, and you can call it a vapor trail if you like. It's almost like if you're watching a movie and somebody's underwater and there's a bullet goes through the water, you see that stream of white behind the bullet. That's what we're talking about here. And if you can deflect the particles in a magnetic field, then you can make measurements and determine something about the particle. Briefly, it's possible to determine the charge to mass ratio of the particles you observe, the tracks they leave. It'll be in a magnetic field, so they'll be deflected in an arc. You can measure the radius of the arc and use physics to determine Q over M. If you're a physicist and you determine Q over M and you go to a reference guide either online or in a book and nobody has ever found a particle with that Q over M before, then you have discovered a new particle. This is how new particles are discovered, primarily. Very briefly, I wonder if I have it open already. I think I don't. It's over here. I'll just show you a quick video of detection. I got to go to my computer to get it to open over here, though. I think this is going to be I don't know, that looks like a bubble chamber. And don't worry about that stuff you see falling towards the bottom there. What you're looking at are these tracks that appear. There was one that was circular here. There's another one that's circular. And the reason they're circular is this is exposed to a magnetic field. So anytime you see a track, and this, I believe this is just background radiation. I don't believe they actually have a source here. It's just the radiation that's continually bombarding the Earth from the sun and other places. So briefly, what is the difference between a cloud and a bubble chamber? A cloud chamber uses a vapor, so something in gaseous form, usually alcohol like ethanol or methanol, that's very cold. So it is almost a liquid. Okay? It is almost a liquid. And things that are almost liquid condense. Right? If the air is very moist and you bring out a cold bottle of something, you get condensation appearing on it. So when that charged particle goes through that liquid, it leaves a series of water droplets or alcohol droplets that leave evidence of its track. A bubble chamber is kind of the opposite. It's got a liquid that's superheated. And it's liquid, but it's almost in gaseous form. But the same thing happens, except when the particle goes through, it vaporizes that liquid that's almost at the boiling point, and it leaves a series of little bubbles. They both leave bubbles in some way. I don't think it's important that you know exactly how they're produced. But now, are there any questions about detecting these particles? Anna?
I don't necessarily have a question about detecting these particles, more so about detecting antimatter. How did we go about finding it?
The question is, how do we detect antimatter? Well, I can only speak to a couple of examples. The one that we're going to talk about here is pair production. So let's assume that somebody has a particle detection kit, cloud chamber or a bubble chamber, and they observe this event. And by the way, they film these and they photograph them. There has to be a record, right? Because you can't, there was a track, what was that radius, and put a ruler down. You need some type of evidence on paper. So there's a lot more that goes into this that it will be a little disappointing for me to just say, don't worry about it. But we happen to know or assume that these particles, when they were created, were moving at about 10% the speed of light. Okay? So there's some event, and by the way, the event happens here, and the two particles move in this direction. Okay? There's some event in nature that happens there. But before, there's nothing there. However, don't forget that a cloud chamber or a bubble chamber only detects charged particles. So if this were a photon, which it is, because this is going to turn out to be pair production. If this were a photon, you wouldn't see it anyway. So how do we know there's an antiparticle there? How are they discovered? Well, you do measurements with the radii. We know the magnetic field because we create the magnetic field. And based on the magnetic field, you can see somebody's put a plus here. This has to be a positive particle, and this has to be a negative particle. Okay? I'm going to come back to your question after we do the problem. The question is, how do we know about these new particles? How do we detect antiparticles? So the magnetic field that these particles are exposed to, and let's assume we don't know what the particles are, we don't know what the event is 30 millitesla, and the initial radius is 5.7 millimeters. What's the charge to mass ratio for the particles? So this is a Unit 2 question, kind of a Unit 2, Unit 4 question. The magnetic force on the particle is equal to the net force on the particle, which means QVB equals mv squared over r. And you can rearrange that and get Q over M equals V over BR. The physics behind setting this up is from Unit 2, but the concept of charge to mass ratio is the beginning of this unit when we talked about Thomson. So we can calculate this. The speed is 0.1 times the speed of light. The magnetic field is 0.03 Tesla. And the radius is 5.7 multiplied by 10 to the negative 3 meters. So let's all grab our calculators and calculate what the charge to mass ratio of each of these particles is. Clearly they go in opposite directions, so they have opposite charges. I'm getting 1.76 times 10 to the 11. Okay. So you're a physicist, and let's say you were a physicist. Did you ever find out the diameter?
It was about 8.5 kilometers.
8.5 kilometers. I was a little high. So about 8.5 kilometers. Not quite the distance from here to Millet, but that's kind of a benchmark for the Large Hadron Collider. So let's say it's, and the reason I remembered that is I was going to ask you, and I'll maybe ask you anyway to look it up again. I'm interested in when positrons were identified empirically, like discovered, not just hypothesized. And don't tell me when you find it, we'll come back to that. We're talking positrons. So imagine you are a physicist in 1940, maybe even earlier. We'll find out. 1940. And you set up a cloud chamber or a bubble chamber. And these events, this event doesn't happen all the time. It's not happening everywhere. You might be sitting staring at your cloud chamber for a while, and all of a sudden, you see those two spirals. And you go, I better take a look at this. You take a look at your film or your photo that you've been compiling, and you do the measurements, and you get Q over M equals 1.76 times 10 to the 11 coulombs per kilogram. Okay, that's a charge to mass ratio. Maybe it's a proton, you say. So I want you to take your formula sheet and take the charge of a proton and divide by the mass of a proton. And when we're doing run-of-the-mill calculations, you don't need to use that 1.674, not 26 or whatever it is. We want the charge to mass ratio, so I'm going to take the charge of 1.6 multiplied by 10 to the negative 19 and divide by the mass. Oh, I really buggered that up. Divide by the mass of 1.67 times 10 to the negative 27. And I get for a charge to mass ratio of a proton this number. Well, that is not what you've discovered in the lab. It's not that charge to mass ratio. You go, well, maybe it's an alpha particle. You probably wouldn't suspect that. But if you take the charge of an alpha particle divided by its mass, you don't get that number. And I need you to understand, I really want you to understand, that table of charges and masses on your formula sheet, that's really limited, right? There's other particles other than electron, proton, alpha particle. But if you take the charge of an electron and divide by the mass of the electron, which by 1930, 40 was known, all of this information was known. In fact, the charge to mass ratio of an electron was known by Thomson, even though he didn't know the mass. Guess what you get? You get that number. So now getting back to Anna's question, and I hope I understood your question properly. This is a little disappointing for you as a physicist because you have not discovered a new particle. But there's another particle with a positive charge, and it has the same charge to mass ratio. And if you were the first person to ever observe this, then I suppose you could be credited with the discovery or the evidence that that antiparticle exists. Now, some of those other so have I answered your question in a basic level?
Yeah.
Okay. Antiparticles may also be created not through natural processes, but you just might smash two nuclei hard enough together, and in the process you get some weird particles coming off that through measurements you determine have an opposite property compared to a similar particle. It is not a simple matter. No pun intended. Thank you. Appreciate that. It is not a simple matter. It really isn't. There's a lot going on. There's a lot of math going on. There's a lot of hypotheses, predictions, some experimental results that put all of this together. So, for example, just to round this out, not for example. To round this out, when we talk about neutrons having things within them, it turns out the forces holding those things together in the form of a neutron are so immense that prior to 50, 60, 70 years ago, we just didn't have the energy input to smack those things hard enough to see those things fly off. But when we see them fly off, they leave tracks in a chamber. Have we got a year for the discovery?
1932.
1932. So very shortly after Dirac hypothesized their existence. I mean, they had cloud chambers back then. I guess they just had to go looking for it. And it also might be a case of the chicken and egg thing. Maybe it was kind of a joint discovery and hypothesis together. Maybe he looked at those tracks and that was his hypothesis. Okay. Any other questions? So anything involved in this lesson that has calculations associated with is not new physics. This is just applying physics to new scenarios, cloud chambers, bubble chambers, particle accelerators. E equals mc squared, which we knew can be applied to matter-antimatter annihilation or pair production.